So, good day. This is a walkthrough for design practice 4. I trust that you would have read the script, and I'll just be explaining what is happening. In this problem, we have a joint that was done that is done similar to what was done in class, for example 2, and we're going to analyze these 3 bolts, A, B, and C, and be able now to get an appropriate bolt size for these 3 bolts. Right, we have some constraints that we need to work with. For example, we could say it's bolted onto thin strips. So we have a guidance as to how big the bolt should be or should not be. If we cross a certain diameter bolt, we could actually tear the strips itself. Right, so we will see how we're going to factor in all these things into this design practice and also into the sizing of these 3 bolts. So the first task that is asked is to create an Excel sheet to calculate the shear stress in the bolt. So this is a sample of the Excel sheet, and we'll be testing the sheet with values for areas of the 3 bolts, and based on the dimensions given in the drawing and the PDF, we will be able to calculate what the shear stress is. Now, everything in orange here are equations, everything, right? The inputs are what is in normal black here, right? We have P, L1, L2, L3 example. These are things given from the notes in class. All the equations, all the formulas are given in notes in class. Those are these notes here. So if you go to joint loading, example 2, this is the same problem we have. So for example, the formula for X bar is given here, Y bar is given, tau direct is given, FA direct is given. So all the formulas that are required in the Excel sheet are given in this note. Right, the K is given. How to find the angle? So the angle will be cos inverse X bar over OA, for example, and to get cos inverse in Excel will be A cos, and then whatever it is in brackets. A means arc cos, which is also how we say cos inverse. Right, so the formulas that are required for the Excel sheet are all given in this example too. So when these formulas are entered, for example, as I said just now, we had X bar, Y bar, tau direct, FA direct, etc. We have all these formulas here. By putting in your values from the question, then you're experimenting with these values here, 176.7, 176.7, 314. Those are what highlighted in this table here. This should be a shear stress calculated. So this is how you test the Excel sheet to ensure that it is working. So that will be the first task. The column C here, this is it in, these are the diameters, but in meters squared. Alright, so I just did a conversion here, and it's a formula in this section here. Right, so this is the Excel sheet, for example. This is the converting the millimeter squared to meter squared. Sigma YP, over in this case here, this is the sigma yield point, or the proof point for grade 12.9 bolt. That is from the fasteners lecture we did. So for this grade material, this is the strength of the material here, or the design strength, or the yield strength, or the proof strength, whichever one we want to, whichever terminology we want to use. Right, and our design, of course, is sigma yield on 2n. Right, and this is our factor of safety here. Right, so go ahead and try and get your equations. So, for example, X bar, again, is taken from your notes. So you notice I use the areas for meters. Y bar, tau direct. Right, so the force divided by the sum of the areas. Right, so use the example 2 equations and complete your Excel sheet. And you can pause the video at this point, and when you're finished, you can ensure that your Excel sheet is working and you're getting your values for shear stress as indicated here. Right, then we will move on to the optimization part. So at this point, you should have tested your Excel sheet and should have gotten the values for stresses. So you should have a working Excel sheet that is giving you the values for your inputs. Now, the next task, task 3, is to determine the maximum bolt diameter permissible by the geometry, using the 1.5 DR assumption in the drawing. So a thin strip of material, as in this case here we have it bolting up to these thin strips. If the bolt hole is too large, then we run the risk of um, tearing the actual parent material. Kind of like something like a file page, and you have the hole in the file page, and if you were to pull on it, it could actually tear the file page. So something similarly could happen. Right, so we have to ensure this bolt or this bolt hole is not too large to cause that to happen. And one rule of thumb is the 1.5 DR rule, meaning that the distance from your edge of the bolt hole to the edge should be no smaller than 1.5 DR on both sides. So this is our first constraint. We have to ensure that the bolt diameter is smaller or small enough to allow this rule. So in order for task 3, we need to get a that actually asks 1.5 dr plus dr plus 1.5 dr is equal to 50 millimeters. So we could solve for dr. Right, I'll repeat that again. 1.5 dr plus 1.5 dr, which is 4 dr, is equal to 50 millimeters. So therefore, we could solve for dr. Therefore, right, we could see dr, we had solved for dr is 12.5. So you need to actually put it in an equation in the Excel sheet. And then you do pi dr squared on 4 to get your area. So this here would be your maximum area permissible. Anything beyond this, we'll be violating the 1.5 dr rule. So the next task is task 4. Locate the solver in Excel and fill in the dialog box as per figure 2. So that's this figure here. So to locate your solver, we did this early in the semester. We go to data. So right now we'll be on home. We go to data. You will see on the NES solver, you would have added the solver added in the beginning of the semester. So this is your solver box here. And then we are now required to complete this box. Right, so take some time. I will pause the video. You could pause the video now and find your actual solver box so we can get started. So now that you have found the solver box, we will attempt now to fill out this actual solver parameters box. So what we are trying to do in this question is get the best or the optimized values of the bolt size. Right? We don't want to go too small for it to fail, and at the same time, we don't want it to be too large so as to tear or violate the 1.5 dr rule. So instead of trying different sizes, we will use solver in Excel to give us that those actual diameters. So in this here now, we have the solver parameters, and the first thing we need to do is set an objective. The objective is what we want to achieve. Right, so what we will do here is set the total shear stress. So what that means is that the total shear stress is the total shear stress in all 3 bolts. So in this column here, or in this cell, we have added all 3 shear stresses. And what we want to do is set that as the objective, meaning that we want to minimize. So we click the minimize button, and we want to select that as our objective. So basically what we are telling Excel is that we want to minimize the total shear stress from all the bolts. Right, so we minimizing the total shear stress, but how are we going to minimize it? We need to be changing some cell. So we tell in Excel, okay, we want to do these things. We want to minimize the total shear stress by changing the cross-sectional area of the bolts and the safety factor. So that's the only way we could adjust or we can manipulate the total shear stresses if we adjust the area, because the physical parameters, the force, the length, those things are set problem by the question. We cannot change the actual geometry of the problem. But what we could do is change the bolt areas for now, right? Because that's what we're trying to figure out. So that we'll be changing the shear area, so you could drag from 5 straight down to 8, hit enter. So we'll be changing the shear area of bolt A, B, C, and also the factor of safety. Because we have it as 2 right now, but if we could come down to 1.5, we could come down to 1.1. Once we're greater than 1, we know that we on the over design sense. If we are less than 1 means that we will be failing. Right? So we want to ensure that n is greater than 1 at least. Right? 2 might be a little too high. Both sizes might be too big. So the next step here now is to enter our constraints. Right? So just to step back, we tell in Excel we want to minimize the total shear stress in all the bolts. Right? The total being the sum of all the shear stress. And how we are doing that, we are changing the cross-sectional areas of the bolts and also change the shear for the safety factor of the bolts that being applied. So we are given extra permission to change the cross-sectional areas and the safety factor. But we must have some constraints. And those constraints are the shear stresses in the bolts must be equal to tower design. We don't want it to cross tower design. Right? The next thing is that, as I mentioned just now, our safety factor must be greater than or equal to 1. And finally, the bolt cross-sectional areas that Excel is changing, it should always be less than what we had calculated as the minimum permissible from task 3. Right? Now, you could achieve all these things. You could achieve 1 and 2, these two constraints, by having a large cross-sectional area. But that's not what we want. We want it to follow the 1.5 DR rule. So the third one here is saying that the cross-sectional area of the bolt that Excel is finding must be less than that given by the 1.5 DR rule. So we will be inputting these constraints now into this box. So under constraints, we click add. So the cell reference, we say tau A, shear stress in A. We want this to be equal to our constraint, and our constraint is our tau design. Enter. So okay. So now we have that constraint there. We could add another one. So cell reference B should be equal to tau design. And then we could add our next one. So we could just click add here. Let's go to the next one. C equal to so now we have those three constraints. So we say any shear stress in bolt A is equal to tau design. Same thing for B equal to tau design. C equal to tau design. So that's our first constraint. The second one is the safety factor must be greater than or equal to 1. So we come to add our cell reference. This is our safety factor. So that is N here. Enter. Must be greater than or equal to, and you could actually type 1 in your keyboard here. So you click OK. So we have here the safety factor should be greater than or equal to 1. And then lastly, we're saying that the bolt cross-sectional area must be less than what was specified by the 1.5 DR rule. So we click add. Right, so for that last constraint, we click add. What we could do, we could highlight the tree here. So those are the three areas, and we're saying it must be less than, so we could put less than or equal to, and our constraint here would be the one you could actually click on the cell where you had it calculated. Right, so we have our three constraints. So again, what we are doing here is that we're optimizing. We are telling Excel we want to minimize the total stress in the three bolts, the sum of the three stresses. Right, so that's why we click the minimize. Excel, you have permission to change the areas and the safety factor. That's what we said here. But you must follow these rules. And these rules are the shear stress in each bolt must be equal to the design shear stress. The safety factor must be greater than or equal to 1 at all times. And the areas of the bolts, the cross-sectional areas of the bolts must not surpass 122. It must be less than that for it to maintain the 1.5 DR rule. So when we fill this box out, we could then click solve. And you could see here we got a solution. So your solution might actually be a little different from this the first time, but you could see here generally if your values are different, that's okay. But make sure that things are where it's supposed to be, meaning that we have our tower design and our shear stresses in each bolt is equal to our tower design as we asked. We could see here that our shear stress areas calculated or determined by Excel are less than or equal to the 1.5 DR rule. You notice for AC, they actually use the exact value. So it kind of pushed to the limit. And you can see how this factor of safety is equal to 2.2. Right, so it's quite large. So that means we within the design, we far within the design, a little bit too much if you ask me. So what we could do, we could say, okay, click restore original values. You could click this radio button here, return to solver, dialogues, click OK. So that will bring us back to this box. And then what we could do now, we could actually modify this a bit. We could say, okay, our factor safety, having it at 2.23 is a bit high, so we could say, okay, change. And we could say our factor safety should be, we could actually set it to something. We could actually make it 1.3, for example, or 1.1. So we click solve. So we actually got an error here. Right, so that error was because I made it the factor safety equal to something as opposed to less than or greater than to something. Right, so solver was not able to give us an exact solution. Right, so I went back to here greater than or equal to 1. If we click solve, we would get our solution we got just now. Right, now if we want to tune this a little bit more, we could add another constraint and say, okay, the factor safety should be less than or greater than, for example, 2. So what we did here, we said it must be greater than 1 but less than or equal to 2, meaning that we confine it between 1 and 2. If we click solve, you could see here that the values were changed. Now it actually decreased the shear areas, and instead of 122 as we had before, now we are a little less than at 110. And our shear stress again is equal to 275. Factor safety is 2. So we could stop there if we want, or we could take the analysis further if we want to even refine this a bit more. Alright, so at this point we got 3 areas, 48.5, 48.5, 110. And as the question says here at this point, you look into table 13.2 of the fasteners notes and to see what bolt size it corresponds to. Right? So this is with a bolt design of factor safety of 2. Now if this is too big and we want to get it to be even smaller, right? Which is in the case in aviation where we're trying to minimize as much weight as possible, then we could go further. Right? If we looked at the problem, we minimize the total stress, shear stress in the boat. But what if we want to now change it such that we have the minimum amount of bolt size? So what we could do, we could minimize the total sum of the area instead of the total sum of the stress. Right? Again, the bigger the factor of safety, the smaller the tower design. And all we're saying is that your shear stress should be equal to your tower design. Right? Now let us try that. Let us try and say, okay, total bolt areas, for example. Right? And that is equal to, make a room here, that is equal to the sum of these 3 areas, bolt A, B, and C. So that is the total sum of the 3 areas. So we could ask Excel now, instead of minimizing the total stress, let us minimize the total area. So we try something different now. We are saying, okay, we're minimizing the total area. Right, so look at what we had. Remember, we had 4.48, 4.48, 110. So if we were to hit solve now with the same constraints we have on stress and factor, safety, and the area, we click solve. Right, so you would have seen just now we got an error message, and that's because sometimes, depending on the Excel you're using, you might be able to get a solution, sometimes you may not. Right, so I'm just doing over the same. I haven't changed anything. Now I found a solution. Right, so what you could do is, if it is you got an error message, you first time you could click this toggle here to make unconstrained variables non-negative, meaning that you're allowing um, values within this region here to go to negative and then back to positive in trying to find a solution. So that's one thing you could try. So you see when I did that now, we got an error. Right, so I click it, now it finds a solution. Right, so keep trying the fun things. Right, now you could see when, the point is here now, when click OK here, when we change the objective from the sum of the total stress to the sum of the total area and we ask Excel to minimize it, we could see the smaller areas we got. Right, so we have 24.2, 24.2, and then 55. Remember it was 110 before. So we almost half the bolt sizes, and that's because our factor safety is now 1. Because we told Excel that it should be greater than or equal to 1. Right, so this here is also an acceptable solution. You can see our tower values is equal to the tower design, and it is less than the 1.5 DR rule, the area. Right, so you could try the fun things, you could minimize the fun things, you could even minimize factor safety too if you like. You can minimize tower design. Right, so the point of the exercise is to experiment and try the fun things and learn about optimization, really. Alright, so at this point here, we close this off and you could probably type in here bolt A and B because we see it's the same size, and you could say what size it is. So look to the table 13.2. Right, so that's the table 13.2 in the notes, and let's select a bolt size. Right, it doesn't have to be what we calculated here, it could be the first one we did. Right, the point of the exercise is really to learn and experiment with optimization and the solver window. Right, and all you're submitting is your Excel sheet for this exercise.